All right, I already. Good afternoon. Today we're going to be talking about permanent restoration of sense of touch. Another chance to feel the world. And I'd like to introduce Mario, Cassandra, Manny, Isaac, and myself, Parag, the principal of this.
So the history of prosthetics. The first use of prosthetics was shown in ancient Egypt at around 1500 BC. It was a leather toe with harnesses, and it was mostly for aesthetic reasons, not really functionality. And from then on, all the way up to the 17th century, little advancement was made in prosthetics. Mostly, like in the Middle Ages, from all the way to 1500s to the Middle Ages, very little was made. And mostly, like I said before, they were for aesthetic reasons or just to cover up a deformity or an injury, not really used like function. And then in the 17th century, European doctors, a French and Dutch one, I believe, made the first advanced prosthetic leather harness and actual hinge joints that would allow you to move. And after that, in 1945, the artificial limb program was made. And this was in response to all the veterans that had lost limbs in World War II. And this is what led to all the advancements that led up to our prosthetics today, like rubber limbs and like that. In this modern day, there are over 1.6 million people with prosthetics, majority of them elders and suffering from diabetes or other diseases like that.
Okay, so we're going to start off by introducing the sensory pathway. This is what we're trying to get. Like we're trying to restore this. So pretty much you start off with a hand. You have mechanoreceptors on there, which detect external stimulus. So if you touch something really warm or something sharp, your mechanoreceptor will pick up to that. And then that will be transferred to the sensory neuron, which will carry the electrical pulse that was created from the stimulus. It will carry it through the relay neuron to the CNS. And then by then, this is the CNS, spinal cord. The relay neuron will then take it through the CNS to the motor neuron, which will take it to the effector, and that will in turn create the response.
So about right now, some of you may be asking yourself, why is this important? Why should we care? The real question you should be asking yourself is, how is this not important? Right now, people out there are living with phantom limbs, and that's where you can feel the pain of when your arm was detached or when your leg was detached. And it's still there, and they're still coping with it, and there's no way to get over that. With this restoration process, they would be able to feel that limb again, so that phantom limb will no longer be there. Removing the wires. Right now, there's a robotic arm, and that has wires protruding from your arm, so you'll be able to see everything. And girls, who likes it when their hair's in front of their face? Really, it's annoying, right? So, I mean, who wants wires on their arm? And then there's also, we want to restore that damaged sense. Again, we're just restoring how you would feel the feeling of heat or pressure or coldness. And right now, I'm going to do a demonstration with Dr. Hutt. Stay sitting. Can you close your eyes? Hold out your hand. Do you feel the warmth in my hand?
My hand feels cold.
Do you feel coldness?
A little bit, yeah.
Do you feel me poking it?
Yes.
What do you feel?
Nothing.
There's nothing there. Open your eyes.
Oh, okay.
Nothing's there. That's what everybody feels. If they have prosthetics, they don't feel anything. Right now, there's nothing there.
So the objective, right? As we were going through the project, we're thinking, what are we doing this? What are we doing this for, right? So, here, the main objective not only is to develop a more efficient prosthetic, but also we have to take into consideration that it would be a life-changing innovation. Another objective that we had in mind would be to develop a microchip that attaches to the nerve fibers, which signal electrodes surrounding nerves. Not only those chips will send the signals, the electric and the signals that from the sense of touch to the spinal cord and everything else. And overall, create a prosthetic that will have an implanted sense of touch. As we were saying, the prosthetics that we have now are not as advanced or not as efficient, right? Therefore, we're trying to recreate the human aspect of sense of touch. We're trying to recreate what they used to have and they lost it. We want to make them feel how they used to. So that is part of our main objective.
Okay, so in order to do this, we have a really lengthy process, and it's also confusing. So we're gonna go through it, and if you guys have questions, please feel free to ask at the end. So the first step will be to create receptors. Basically, what the receptors will do is detect the external stimulus. These receptors will be placed onto the prosthetic and will color coordinate them. So we'll say like the receptor, if it's red, it would be responsible for feeling heat. If it was blue, it would be responsible for feeling cold. And then if it was pink, it would be responsible for pressure. And then the receptors, once they interact with the stimulus, they'll send an electrical impulse to the first chip, which we have to create in the second step.
Okay, the second step would be to create the first chip. The first chip will replace the first order of neurons that were affected. Obviously, if you have no arm, you have no neurons anymore, right? So that would replace the sensory pathways and receptors that were lost. The other one would be to receive and send signals, impulses to the second order neurons that are intact. The first one that would be implanted in order to replace the one that was lost will send signaling to the one on your arm. Let's say my arm was cut off here, right? I don't have any more. So we would implant one over here and send from there over here, right? So we will make a connection between the signaling and the receptors. Now, another one would be to assess the conductions of impulses throughout the prosthetic. As I said right now, it will send signals all throughout the arm, receive and send electrical impulses.
Before I go on to that, I'd like to say that there won't be a chip here, it'll just be in the prosthetic. But there will be a second chip. But before I get to the second chip, I'm going to tell you about the second neuron pathway. The second neuron pathway is located on the spinal column. And from the spinal column, it receives the sensations from the first chip that we'll be creating, and it'll come to here. And the sensations, we don't know what the sensations are yet here. But they'll travel to the brain, to the thalamus, and the thalamus interprets the sensations as movement or pressure or heat or cold, and it'll send them back down to the second neuron pathway to either the motor neurons or the sensory neurons. The creation of the second chip will be looking like a long, slender nerve fiber. No, you're good. It'll be located on the spinal column. It will have built-in Wi-Fi, so it can interact with the first chip. So the first chip will be able to send the signals that it receives from the receptors to the second chip. The sensations will also be sent back. This chip will be a send receive chip. So you receive the sensations, the brain interprets the sensations, and then sends them back.
So our fourth step would to create the third and the final chip, and that would mimic the function of the motor neuron. And so once the second chip receives the signal, it will send it back to the third chip, and then it would mimic the motor neuron, which would react to it. So you'll feel the initial sensation that stimulates the first chip. And so if everything goes according to plan, it would feel as if the prosthetic isn't there and it's like the original one.
And lastly, the last step, this is where we put everything together. You're gonna have the first chip, which is gonna be in the arm, and this is where all the sensory input comes in. And this will send all the information to the second chip, which is in the spinal cord. And from the spinal cord, it will relay the information to the brain, and the brain will interpret it and relay it back. And from that chip, the third chip, which is also on the prosthetic, will act as the motor neuron, and that is what tells the mechanical arm to move and squeeze, things like that. And also on this step, this is where we'll be trying to minimize the wires shown and just make it more ergonomic and more easier for day-to-day use, basically.
And then overall, the process that we talked about at the very beginning, the sensory neuron pathway, it's just exactly like this, and it would be back to the first one. So our results, the prosthetic limb should act as a normal limb. Sensation, we're expecting that to be bad, as well as mobility, full range of motions with the prosthetic, and then the absence of the phantom limb feeling, whereas like the pain that you feel where your limb wasn't like attached to you, that pain would be gone. And the positives out of this entire proposal is the sensations restored. We finally gave someone another chance, like, to feel the world again. It's not like hearing aids. If you lose hearing, you have a chance to replace it. This is something else that's really like we're expecting it to happen, and we're expecting another replacement for another sense that's potentially like one of the most important senses. It has full mobility of actions, and then you can, like when Dr. Huck was asked to close their eyes, if we had asked someone to close their eyes and identify the shape of an object that's in their hand, they would be able to identify exactly what that shape is, like a circle or a square, whatever it is. And then the person should be able to return to their normal task, like daily tasks, being able to not like feel like a handicap. They should feel able to do whatever they're always been able to do. The negative of this is pretty much the length of this process is really long, which we will talk about in detail. And the reason for that is because each person has a different neuron pathway, and scientists would have to map out each individual's pathway in order to create this whole, to make this whole sensation restoration process go through.
And they took the time to create from raw materials to actually creating the first chips and everything would be around 5 to 6 years, because we do have like the raw materials and like the wiring to make sure everything connects to each other so it can function properly. And also they'll take an additional 3 or 4 years after we have made the initial prototype, because like you said before, that everyone has a unique neural pathway. So we were trying to make it so that you wouldn't need to adjust it as much for every individual to use, and also to make it more comfortable for everyone to use, because you don't want, like I said, wires hanging out on this person. Our resources are, obviously none of us are neuroscience majors or engineers, so we would need neuroscientists and biomedical engineers to create the chip, but not medical engineers would actually create the chip, and the neuroscientists would aid them in how they function and how they all connect together. And we would also need 2 areas where we would work in: a scientific laboratory to create the chips, and a medical exam room kind of thing to actually do the test trials to make sure everything works and that the wearer is comfortable wearing it. And the estimate cost would be $250,000 to $1 million, because it is a lot of materials and it is a long period of time, and we do need a lot of people to help out, so it would be very costly. Question?
None?
My major concern is like, how small is this chip gonna be? You know, the one that's gonna carry the Wi-Fi. Like, how, like, you know what I mean? How small would that chip be?
It would resemble the fiber, so it would be relatively
Very,
small.
very, very small. So
Very
like,
small.
and the only like the major setback I have is like the Wi-Fi being implemented in something so tiny. You know, like a neuron size. How big do you put Wi-Fi in that? You know what I mean?
See, the thing is for the chip, our location of that is the spinal cord, because if we had chose to put it on a cell, the cell could like degenerate and
Yeah.
that would cause the chip to like.
So the
not
Wi-Fi is gonna be
function
on the spinal cord.
Yes.
So yeah.
Okay,
exactly.
so it doesn't have to fit in the
Like
spinal
that's why the chip with the Wi-Fi will
Will
be.
be on the spine.
Yes.
That's good.
I have 2 questions. First, who is your PI? And
Rob.
Rob. P-E-R-A-B.
P-U-R-A-B.
And okay. Other one was how, if you have to make an estimate, how long do you think the person will be able to get back to normal function? Is the prospect that it's completely
It should be right away. They should, like, after they map out and put it on the chips, and they should test it maybe a week of testing, and after that, they should have full ability to be on to the road.
Because during the whole length, like the whole 4 to 5 years, we're going to be running trials and errors, and during that time, we'll be able to figure out what's wrong and what's not working with this specific person's neural pathway, like what miscommunication is there between their pathway and the
So how does, and I'm just betraying my knowledge, my lack of knowledge about the body, but like, so you got this chip. How does the chip talk to, say, just pick one, nerve basically that goes up to the brain, right? So you get the signal to the brain so then it can come back down and, affect the effectors. Like, how does this chip, like, talk to, like, what energy or force allows it to talk to the nerve and send a signal up the nerve? An electrochemical signal, right? Because that's how nerves work. How's that work? Or is that just like too hyper-specific technical questions?
I'm trying to
Because I'm trying to think, there is some chip technology with ocular cochlear implants. And I've always kind of wondered, and they involve a chip that somehow can talk to certain pathways, circuits in the brain, right, to give you the percept of being able to hear. But it's like I've never understood, like, how's this little thing talk to this tube of flesh, basically, of tissue. Well, I'll Google it after it.
Will they like affect certain pathways? So like this chip will send like a certain chemical that will, when it hits like the synapses, that chemical will tell something else to send out different
How
chemicals.
does the circuit talk to a chemical or make a chemical squirt out? You know what I mean?
Yeah, it's really crazy.
But I feel like at that point, it would be more, like you would be taking away from the humanistic of the person and putting more of a robot type thing.
Yeah.
Because this prosthetic, it's not going to be rubber, it's going to be robotic. So I think putting in the mechanical implications into the human would allow it to overcome the chemical conflicts it would face in order to send electrical impulses from the prosthetic to the brain to perform the response. That would be my best answer to the knowledge I have.
Other questions? No? Well, thank you very much, guys. Well.